All right, first, I guess quick show of hands. How many have heard of Facebook before this conference? Or heard of Gluster before this conference? Okay, good. And how many have used it? How many currently use it? Okay, that's not bad. How about Ceph? Okay, Hadoop? All right, cool, cool. Just want to see the audience so I know where to not spend time or spend time. All right, so my name's Richard. I'm a production engineer here at Facebook. I've been at Facebook, I guess, almost 5 years and kind of seen Gluster transition from what my original manager called the science experiment to now production use. So it's kind of the quick agenda of the talk. Well, I'll kind of like give you, for those of you who have really not any experience with Gluster, I'll give you kind of like a 3-slide crash course in what it is and how it works. And that'll hopefully give you some context for the rest of the presentation. And then I'll go into some deployment styles, how we have used Gluster at Facebook, how we currently use it, and how we deal with things like NFS. And then I'll go into kind of like the two kind of broad areas of where we've had scaling challenges. One in operations, and the second one is like the actual core code of Gluster, or the internals, and some of like the changes we have had to make. And if we've got time, hopefully we'll get into some questions. So first, I just want to acknowledge the great team I work with. These are the 6 folks that I work with, or 5 other folks I work with every day. Open source is fundamentally about being in a team, and kind of our team is no different. So I'm really representing a body of work done by these people today. So I just want to acknowledge that. So first, the hook. Here's some numbers of Gluster at Facebook. Data sets range from gigabytes to petabytes. Individual clusters can have on the order of hundreds of millions of files and billions of files if you go across clusters. In terms of QPS, or in Gluster we call them FOPS or FOPS, it's tens of billions per day. And namespace sizes, this would be like a single volume. They can be anywhere from the terabytes to into the petabyte range. And bricks, which is kind of the unit of storage in Gluster, we have thousands of them. So this is kind of like what we have to deal with. And here's kind of a quick like lineage of Gluster at Facebook. We started out at 3.3. At a prior life, I had started with 3.2. And then we, in 2013, moved to 3.4. And then last year, we moved to 3.6. You'll notice we trail mainline. We do this for stability reasons, and I can kind of touch upon our development cycle a little bit later, but we typically will be like a version or 2 behind. And clients into one cluster will have tens of thousands of clients, and I'll get into like how we actually accomplish that a little later. So first off, we'll go back even further. The origin of Gluster itself, this is about open source after all. It was created in 2007 by GlusterFS Inc. The founder and original author was this guy named AB. He's been really good to us and the whole community. And this was acquired by RedHat in 2011, and they've been, I think, a really great steward for Gluster. In fact, I don't think I could have asked for like a better acquirer of that company to kind of carry it along. And they put a lot of resources into Gluster now, which is really good to see. So okay, as promised, here's like a high level of Gluster. There's really 3 basic ways to get data in and out of Gluster. You have fuse mounts or fuse clients. You have a GF API, which is pretty much what it sounds like, a direct API into the cluster. And then you have NFS. And on here you can see kind of the 2 important translators. So translators in Gluster are basically the modules inside the software stack that we divide up the functionality inside Gluster. So if you're familiar with like GNU Herd, it's basically an idea stolen from that project, and Gluster uses it. 2 important translators to really understand are the distribute translator, which is effectively doing sharding. If you notice things like memcache, it's the exact same idea. And the replication translator, this is what provides you the high availability and replication of the data. And here we're just showing like a simple cluster with 3 shards and then 3 replicas inside that. So replication translator, we'll start off with this first. Effectively how it works is you got a client that's doing I/O. It's updating what inside Gluster we call a journal. What it really is little entries into extended attributes and individual files. As you write to files, it's effectively just counting how many write operations or metadata operations you're doing to that file. And they use something called the wise fool algorithm, should a node to fail, to figure out like, where do I go to like reconstruct this data when this node comes back? And it basically makes a little matrix, figures out based on this, like if it's a 3x replicated cluster, a little 3x3 matrix, and it's going to figure out based on this Weisful algorithm which node to actually heal from. So in this case, it's going to pick brick 1. Okay, the distribute translator. This is basically just using ring hashing, and it's very similar to say what memcache does. In Gluster, we implement this at a directory level. So if you ever wonder why Gluster has directories on all the nodes, this is the fundamental reason why. We create a directory, it creates a hash ring based on how many nodes are in your cluster, and encodes that again in extended attributes across the cluster. And these are inside Gluster what we call subvolumes, or you can think of them as shards. And when we actually do file I/O, we basically take the file name, we hash it, and we figure out which subvolume it should go to. A lot of the code of, some like, I think it's 500,000 lines of code in Gluster is really, this all sounds really simple, but where Gluster has all the work is like, what do you do when you rename things? What do you do when you are growing a cluster, shrinking a cluster? All of this gets like really complicated. So at Facebook, when I started about 5 years ago, there was a lot of proprietary storage used for POSIX. Truth be told, we still have some of it, because there's still some really hard use cases out there that we haven't been able to handle with Gluster, though we're still trying. But one of the fundamental reasons that kind of drove Gluster to adoption was really like the speed we could move. Facebook culture is all about like moving fast, and when something goes wrong and you have to like explain to a customer that it's going to take like potentially hours to diagnose because you have to go talk to a vendor, or potentially days to actually come up with a fix. This is like a non-starter, especially when you're like working with other teams across the stack that they're literally fixing things like getting hot patches out within hours. So this was something that, in terms of like the POSIX storage at Facebook, we wanted to like move in that direction. So the other thing that really drove adoption is in the data center. So although our clusters did not look like this kind of like highlights the issue of cabling. And there are kind of like two important cabling systems inside data centers: power and networking. On the networking side, most proprietary storage systems have really custom cabling. They're built from like the ground up. They have dedicated backends like InfiniBand or Fiber Channel. And these are like, and because these systems are not ordered frequently or turned up frequently, it's really hard for your setups guys to kind of like remember how to like cable this stuff up. So you either have to like bring in the vendor to actually do it, which takes time and coordination. And then the other component is power. At our data centers, we're using 277 volt power now, which is more efficient. And a lot of the vendors are simply like not on board with that, because frankly, a lot of other folks out there are still using older style power systems. With OCP, we're trying to kind of like push more adoption to this, but really the state of affairs of in terms of the storage world is they're probably going to be like the trailing end of this. So the final thing is money, like cost per gig. Like this is like what everyone always thinks about when they're thinking of storage. And the accountants get out their spreadsheets and they're trying to figure out how much stuff costs. And if you start ordering, and like POSIX storage systems are not necessarily the cheapest thing in the world. They're actually like, POSIX in general is actually pretty hard to solve and do it well and do it at large scales. So you pay for this. And the ability to kind of drive the cost down by using commodity hardware is actually like obviously really appealing. So our customers, and this kind of like, these include like new customers as well as like the existing customers we had when we originally started. And we have a wide range of customers. Many teams that could simply be like R&D. So these might be like teams that are working on AI. They might just be a team that they have an idea. They don't really know like what they're going to do with it yet. So they don't really want to invest the time on like, say, writing a object store API. They just kind of want to like throw some ideas around, write some C++, and like figure out, hey, is this actually going to do what we think it's going to do? And then maybe they might stay with Gluster, or they might like move on to like something like HDFS. And those that stay on, they go into like basically full production workloads, and they're supported as such. So in general, they're like, and we also have like the classic POSIX general purpose clusters, where these are like, they kind of look like your maybe your average NetApp where you've got like just a slew of unstructured data from various teams. Could be spreadsheets. It could be just, could be media. It just runs the whole gamut. And you can kind of like further kind of refine this into like 4 different groups. So you have archival, which is your classic backups, and then you've also got like the glue, being the glue between large-scale systems. This is like another important use case. So say you've got like some huge data warehouse application. It's going to distill that data down to maybe only a few terabytes from many petabytes, and then that's going to be injected into some database. Generally, these systems don't talk well to each other, and we use Gluster to be the glue between those systems. And then finally, anything that kind of doesn't fit into any other store solution. So if you're not like media, you may not fit into something like Haystack. If you're not like, you don't look like really databasey, or maybe you were on a database, but the database guys yell at you because they're like, what the hell are you doing storing like a gigabyte, blob in my database? You might get booted out of that, and they're going to tell you to go find another home. So basically, if you don't fit anything in these other boxes, we're usually going to take you on. Here's another way of looking at it. You can look at this as like I/O size and data set size. Haystack, HDFS, cold storage are at one end of the spectrum. And then you've got MySQL at the other side, and RocksDB. So these guys are typically very small I/Os for like a transaction, and the data set sizes are generally like gigabytes to terabytes. Using some sharding magic, these guys can also obviously get into like the petabyte range in the case of MySQL. And then you've got us in the middle. And we range from like data set size in the gigabytes all the way into the petabyte range. And our I/O sizes are generally, they can be anywhere from 4K to 2 megabytes, depending on what kind of request sizes they're using on NFS. So hardware, you'll probably have no surprise here. We're using OpenVault, which is an OCP solution. That's what one of the Gluster trays looks like. And currently we're using 4 terabyte drives. We have 30 of these in a machine, which is 100 terabytes usable per host. We divide these into 2 RAID 6 groups. We also have some other hardware that we use, which are kind of like hybrid systems. They use, it's a hybrid of flash and a RAID 10 volume. These are kind of for like hybrid workloads that maybe require, like they've got a lot of hot data that they need to that needs to be accessed very quickly. The Gluster community is kind of working on other solutions to this around cache tiering. You're going to see that. I think it's showing up in like 3.7 already, and I think it's going to get more hardened in 3.8. But we kind of like to experiment with both ways. So right now on some of these hybrid systems, it's really like block level caching, whereas that's going to be more like file level caching. These are nearline SAS. Yeah. So it's basically the controller is enterprise, and then the platter will be more consumer. Yeah, RAID 6. Yeah. 15 and 15. Yeah. Yeah, so underlying file system, we use primarily XFS, though we start to use ButterFS as well, but we're kind of like, we have probably maybe 20% of the fleet is in ButterFS. We're kind of like letting that mature a little bit. We've seen some performance issues with ButterFS. So the majority is still XFS. No, hardware RAID. Yeah. We are experimenting with software RAID right now. The big question there is like the write hole, as well as being able to like journal things very quickly. Like NVRAM is like obviously really nice when using a hardware RAID card, and it's actually a really tricky problem to get rid of it. In terms of the vendors we use, it'll be like that. We do multiple vendors, so it would be, I think, LSI and say PMC Sierra, which is I think now owns Adaptect. Yeah, we use all the standard tools. Yeah. So if you want to look at like what a Gluster cluster looks like at Facebook, this is the general purpose clusters we use. We basically have subvolumes that go across racks. Here we're showing like, the positions are perfect, but in a real data center, we don't really care what position it is in the rack. And we'll have, in the case of OCP hardware, it's going to be 9 servers per rack. So we have 9 subvolumes per rack, and then we just like stamp these things out. So in terms of high availability NFS, a lot of people always ask us, like, how do you guys do it? There's a lot of different options for this. I really just suggest people use what they're comfortable with. We happen to use CDDB to do this, and it's just a really small piece of software out of the Samba community. Its job is really to just move IPs around when a host fails. And I'll give you kind of like a quick rendition of how it works. We have some file going to some node. That node dies, and CDB is responsible for moving that data over to, or moving the IP addresses over to the other nodes. This all works because NFS v3 is stateless. If you do not believe me, try this out with Gluster. It will work. You'll get a brief pause, and it resumes. If you really want to drive down to the stack, why it works is it comes down to the structure of the file handles. In Gluster, they're completely deterministic. You have a volume ID as well as a GF ID encoded into the file handle. And because of that, any node can answer requests for any other node. So this is kind of one of the beautiful things that they've done in the design of Gluster. These are the NFS daemons that would be structuring the file handle in this way. Yeah. So this all works, but like, what's kind of like, if you're looking at this and you're with a critical eye, what's kind of like a problem with this kind of method of HA NFS? Anyone got any ideas? Yes? We don't support that, so not a problem for us. In what way? No, not really too much of a problem. Okay, so no, because again, Gluster's got internal locking on the back end of the bricks, which will maintain the consistency during these failover events. Well, the real problem here is like this all works great within a rack, but what happens if a whole rack fails? It's a rare event, but it's like for most people using a file system or designing an application on a stack like this, it's an event they probably want to know what would happen. And for a while, we didn't really have an answer to this, so we then started looking for other options. And this is basically what we came up with. And this is basically stolen with how a lot of other systems load balance. So like, this is kind of a very classic setup for the webbies at Facebook, and I'm sure like a lot of web server systems out there. Is just using, you have a bunch of machines, they all advertise an address over BGP, and there's a load balancer that's going to direct traffic to these machines based on some sort of a heartbeat to detect whether the systems are up or not. For us, we needed some tweaks done to the way the load balancing worked for Gluster because we needed like very static assignments for host port and source port, meaning once the session was established, we wanted to make sure the traffic kept going to an NFS daemon because although failover is supported, you don't want to be failing over every single packet. And effectively how this works is node dies, it'll stop advertising, and another rack of nodes will go pick up that traffic and the I/O resumes. Okay, so that's kind of gives you an idea of the deployment styles and how we do things like HANFS. I'll get into some of, I guess, the scaling challenges that we've had. And so in a prior life, this is really what I had to deal with. And you can get away with a lot when you're, dealing with one rack, maybe two racks, maybe three racks. So my mentality was quite different in terms of like what I should be doing with automation and things like that. Because if a brick died or an NFS daemon died, it was like, pretty rare event. You can, maybe put maybe a cron job in there to kind of clean it up every once in a while. Then my boss took me for a data center tour. And this is what this is what I saw. And suddenly realized that none of that's going to work. And, after you like calm down for a bit, you start to like think about like, okay, you got to really like change the way you're thinking. And as I kind of mentioned, there's kind of like two broad challenges, scaling operationally, and then kind of handling any deficiencies inside Gluster itself or the internals. So operationally, the first kind of thing you'll figure out, or you should figure out with Gluster is like, okay, am I going to build like this one giant cluster and I'm going to like shove all my data in there? or am I going to do something else and maybe make smaller clusters? And they both kind of have pros and cons. You make one big monolithic thing. This is, a lot of the Hadoop folks do this. They've kind of really designed a stack that like literally can do like hundreds of petabytes. It's a pretty amazing accomplishment. Gluster fundamentally it's not built that way. It's not designed that way. So instead of kind of like working against it and trying to like force it to do things that's not really well designed to do, we kind of did like what came naturally for Gluster, which is you really do a celled approach. The cons to this are, of course, that you've got to you have more widgets. So you have to like you have to be really good at things like configuration management, provisioning. Like these cells really need to kind of like run themselves because you're probably going to have a lot of them. The pros, there's some pros here too. You've got like great failure domain, like great isolation in terms of failure domains. So instead of like if a name node dies in the Hadoop world, it's like complete tragedy. And hopefully your failover mechanisms work, but if they don't, you're going to have like huge amounts of data that are unavailable. With a system like this or a cell design like this, at worst you might have like a few petabytes unavailable. But the rest should be A-OK. So in order to kind of manage all these cells, the first thing we did was like, the cell really needs to like, or the cluster, if you will, needs to like really manage itself. And we built this tool called AntFarm to do this, which is really a cluster manager. If you're familiar with Haketi in the Gluster community, it's really going to be like, designed to like take over this role. This is something we chose to design in Python and completely external to Gluster for some pretty important reasons. So first, some teams will take approaches to like actually kind of like fork a project, make a lot of like internal modifications, like modify things like even the logging structures to like pump data instead of using like the standard C logging libraries. They might use like a Facebook one. And there's some advantages to that, but ultimately you're kind of like, one, you're forking, and two, you're marrying yourself to things that the open source community is not, has no idea if it exists, and they're certainly not going to support it. So being kind of a big open source fanatic, this is not a direction I want to go. So anything kind of like specific to Facebook, I wanted completely external. It had to like, the core of Gluster had to be pure. It had to be like still fundamentally the open source product. And AntFarm was really designed to kind of like, to basically take the Facebook functions and encapsulate it somewhere. So fundamentally, AntFarm will do performance metrics, configuration management, as well as monitoring or alarming. And there's two components. You've got a manager node. There's one per cluster. It's elected based on a Bully algorithm, super simple. And then you've got everyone else is basically who's not a manager is just a worker. And there's basically master tasks that the manager will do, and then there are slave tasks which the workers will do. And who does what is basically like, if it needs to be coordinated, it's pretty obvious. The manager should be doing it. Uncoordinated, and, the workers can do it. Coordinated activities would be like turning up a cluster, doing, if a node needs to be replaced because it's been out too long and maybe a human didn't like go figure out what's going on or setups took too long, the manager can coordinate that too. Uncoordinated activities is the node comes back from imaging, it needs to put itself back into the cluster, announce to the cluster, hey, I'm back, I'm ready. That does not need to be orchestrated by a manager, that's just worker can go do that. As well as submitting statistics, it obviously doesn't need, host level statistics can just be sent on by a worker. So one of the other important things it does is enforcing layout. So we support 3 different types of layouts. We have what we call off network, which is probably the more common inside pretty much probably the Gluster community itself, which is no replicas are ever in the same network, or in our case, rack. And the pros for this are high resiliency, high read rates. The cons, less write throughput. But say a customer comes along, they're like, I really need high write throughput. You can give them the in-network layout, which is basically putting replica groups always in the same rack. You first tell them they're insane, they're probably going to have unavailability and durability issues. If they agree, this is what they get. Great write throughputs, but not as good read throughputs. And you may have an engineer come to you and say, hey, I know what I'm doing. Let me set up my cluster however I want. For that, we have ordered. I'm not really aware of anyone that uses this anymore, but we support it because, hey, it's America. Everyone. All right, so we are growing and growing and growing, and things are going pretty good, and we're getting more and more clusters and more cells. We finally get to a point where we're like, okay, holy cow, this is this is actually becoming a lot of work to turn these things up, and managing things like provisioning, and when imaging fails, a human would have to go and figure out what happened and try and get it going again. We use things like Kickstart to do imaging, which is pretty automated, but when you have a lot of this going on, it eventually doesn't scale. So JD was created, and it's designed to basically be as AntFarm is to hosts, JD is to clusters. And it does things like provisioning. It'll shepherd machines through the provisioning process. It'll actually create the initial cell configs. And it's going to actually hand things off to AntFarm to actually go create the clusters. Eventually, we're actually going to be having JD monitor metrics, and kind of what the vision for this is we actually don't want humans to actually be turning up cells at all. We actually just want humans to basically be feeding the monster with machines, and it will turn up the cells on its own by just monitoring metrics. So if a cell gets full, maybe it's 70% full, boom, go create a new cell. We don't need to know about it. Our CapEng guys may not like this plan, but they don't need to know. Some people have actually said that, but I don't know, we'll see. When I get talking about Haley, then you might start to get scared, but that's coming. Okay, so there were some code changes for operational reasons as well. The first kind of obvious one for us is we're a big IPv6 shop. Gluster did not do IPv6, so we added that. This is kind of one of the few patches we have not open sourced. We did not open source this because, frankly, probably not all of the world needs IPv6 support, and we did it in a way that makes all of Gluster IPv6. So we actually removed the IPv4 support out of it. So AntFarm, we were looking at it, but then Haketi kind of came along, and we feel like Haketi is really a better approach for the community. The question for us really become: do we move to Haketi or do we continue on with AntFarm? But we actually think it was a great approach that the community took. This one we have given to the community. I'm not sure if you'll see this in 3.8 or 4, but actually I think the RedHat performance engineers actually really like this feature. You used to be able to actually have to run start this performance command, and then you'd stop it and it would dump out some stats for you. For us, we are Facebook is crazy data driven. The engineers are even if they don't aren't owning the Gluster clusters, if something goes wrong, they want to see metrics. They want to know why. This is really ingrained in our culture. And for a long time, they're this thing is a black box. I can't tell what's going on. It really frustrated engineers. So we modified the IO stats translator in Gluster so it could run full time. We got rid of all the locking in this translator. And then got it to dump things out in a JSON format, which is kind of digestible by almost any kind of monitoring system you can think of. And from this, you get something like 3,000 different metrics every 5 seconds. So it's more stuff than you probably even know what to do with. We didn't stop there. We actually went for FOP sampling. We want to know, again, data-driven. People want to know, what are my worst case service times? In order to do that, you really need something like sampling. Now, of course, in a file system, you're doing billions of operations or hundreds of thousands per second in the case of Gluster. You need to sample these things. So we created this FOP sampling feature into the IO stats translator as well. This has been open source as well, and we gave this to Red Hat. So another challenge we had, which is kind of it's not operations, but it kind of is, which is really this kind of this notion people have around NFS. And I was kind of naive to this before I came to Silicon Valley. I don't know if this is a Silicon Valley thing or an everywhere thing, but it's this notion that NFS is evil, it sucks, it's horrible. If you use it, disaster will be upon you and your family. and it's kind of an odd thing. And when you really get down to it and you kind of like unwrap what people are really pissed about, like NFS is just nothing but a set of RPC calls. And it's actually like, pretty nice. It's stateless. It's actually really clean. It's well documented. It's really old. Frankly, I kind of challenge people that whatever you plan on replacing it with, it will probably still be here when no one uses what you built. Why do people hate it? They use mounts, and mounts are easy. They're originally designed for local use, and the standards of mounts are as such. People expect local-like behavior, and when things on the network go wrong or things over the network go away, these are not good at communicating to users like something went wrong, what should happen. Hard mounts make that even worse because it doesn't even give you any kind of an error. It's also bad for other reasons. You have to when the kernel, if there's a kernel bug, you have to upgrade your whole kernel. Well, if you have 1,000 machines, start to go to a customer and say, yeah, no problem, we've got a fix for that. Just upgrade and roll 1,000 of your machines. They're probably not going to do that. So looking for a solution for this, I looked to the open source community. And sure enough, this guy, Ronnie Salzberg, he wrote this thing called libnfs. And this really kind of, I think, broke the, or really allowed us to prove to people that, it's not NFS you really hate. And we did that by making CLI utilities that expose NFS as a CLI. So if you want to get data in and out, you can cat it or put it. You don't need a mount anymore. And it made NFS look and feel like things people really like to use, like the Hadoop CLI. And it also gave people, and then once we finished writing all this stuff, it provided demo code. So if you want to actually embed libnfs in your app, you could. So in short, it really gave people an option beyond mounts. And I think that was just giving people choice kind of really brought down a lot of the tension. So here's kind of a quick demo of what these utilities look like in action. You've got, NFS ls at the top, just showing there's nothing there. We're going to echo some data into a file, and then we list the file, cat the file, we delete the file, and we ls and show it's not there. So this is basically what it allows you to do. No mounting. It's completely user land. If there's a bug, you can upgrade this in user space. It's really nice. This guy we've been meaning to open source. It's really on me. I have to get this working with auto tools and stuff. But what we're going to do here is we're going to offer it to the libnfs guys and hopefully be a part of libnfs itself. So if you compile it, you'll just get these for free. Okay, so back to internals and scaling challenges. So kind of one of the things that we went to, there's actually the first Gluster Development Summit last year, which was really awesome. Looking forward to this year's. And one of the things we kind of brought to the developers was pragmatism over correctness. This is kind of the philosophy we have as Ps at Facebook. And an example I can kind of give you on this is this code snippet. Any ideas why this could be a really horrible thing to do? I'll give you a hint. Okay, so what this is really doing is when you connect to an NFS daemon, this thing is basically having it pick a privileged port. And this is actually in the Fuse code. So this is originally the Fuse clients on our stack used to do this. And as our customers were growing and growing and going, we found that man, mounting is getting slower and slower and slower. And we were kind of trying to figure out why. So we dug and we dug and we dug and we found this beautiful piece of code. And since the days of a Raspberry Pi are here that you can get a 1024 port and below for $10, I have no idea why people even bother putting this stuff in their code. Although it's correct, if you look at the NFS spec, this is what you're supposed to do. It's kind of insane. So people need to kind of as developers, I think they need to kind of at least put an option to say, yes, I've satisfied my, the correctness of the spec, but I'm going to give you an option to get rid of it for performance reasons. Oh, and another example we found is actually on DNS lookups. We actually found that DNS lookups were happening for every inbound connection. And this is something, although again, correct, and there may be reasons you may want to do this for security, doing this inline, not very scalable. And we've got like little pieces of C code that can prove that you can do thousands of TCP connections in the blink of an eye. So like you can scale really huge numbers, even serially, if you avoid some of these issues. So anyone who's set up Gluster before, have you ever seen this? This is like an I/O error. This is probably one of the first things people see and hate. And if you go through the Gluster docs, they will quickly tell you that the way you solve this is you go to the back end and you go figure out what file you really want, and you pick that one, because this is basically split brain. You've got 2 or more copies of the file, and Gluster doesn't know what to do. We saw this pretty soon after not even getting that many hosts going. So probably we're in like the hundreds of bricks, this stuff we start to see. And we knew this was something we need to solve. And as it turns out, when you actually go ask a customer and you say like, well, which one should we pick? They'll either say, I don't know, they'll say, I don't care, or they'll say, pick the last one. Pretty much what a human's gonna do, right? They're gonna pick by size, they're gonna pick by time, or they're gonna pick by majority. Like 2 are the same, one's not, pick that one. And we basically modified AFR to do just this. And you can see here, it's called favorite child. And you can see there's a split brain on the back end, and we resolve that automatically without any kind of I/O error happening to the user. We do log these things, so we want to know when they happen, but the key here is we want to provide availability to the data, or for the data. And lately, one of the other things we're kind of like tackling to kind of like go next level on this is at the DHT level. We just finished a patch to actually handle really exotic cases where you may have like shards disagreeing with each other in terms of what the hash ring might look like, or what the GFID is on the hash ring. And we can resolve these cases without any kind of data loss. So, yeah, in this case, we're picking by size. Yeah. So traditionally, typically what we do is we use the majority policy. So we'll pick the majority case, and we'll go with that. And since we implement this, we've really never had any customers come to us and say, hey, you bastards, you lost my data. It's been actually working pretty good. So the next thing we had issues with was access control. And if you go look at vanilla Gluster, and you're not, say, Ganesha is now an option. I'll throw that out there. But vanilla Gluster, this was kind of what you had to live with, which was this like auth allow, auth deny system where you give it like a list of IPs. You can even use wildcards, and it would, yay or nay access into an NFS daemon. This, when you're faced with like tens of thousands of clients, you can clearly see this doesn't work so well. So we hired an intern. And we said, hey, intern, solve this problem. It ended up being like a really good compartmentalized problem for a summer. And it's kind of like already a solved problem out there in industry, and there's a lot of like well-defined ways of solving this. And we chose using net groups to do this. And it was something that we actually had used on enterprise systems. So we knew it worked, and we had a lot of infrastructure in order to kind of like generate net group files. And effectively how it works is we take, you define an export file like this, and we have a job in the background that basically just scans these exports, and will create net group files against a really huge database that knows in, say, a tier called, a host scheme called my tier, for example. It'll figure out what all the my tier hosts are, and it'll generate a net group. This is then sent to the machines using Chef, actually, and from there, this actually like scales, and you can actually like control access on thousands and thousands of machines. Which are in turn limiting access to, hundreds of thousands of machines. Okay, so another internal thing, this is probably one of the scariest charts a PE at Facebook can be faced with. I would wish this was like, dollars in my bank account on the side, but it is not, it is memory. And this is a memory leak. And probably last year and the year before, kind of a lot of the low-hanging fruit problems were being solved, and we were faced with stuff like this. And, at the beginning, we really didn't know why this stuff was going on. You would find this, you'd find maybe a brick that had high CPU, high memory, you might re-kick it, maybe do a state dump beforehand, and it would drop down, and then it may stay down or it may go up. But this was really bad, and machines are running out of memory. This is even worse than like a machine dying because it's kind of like hobbling. And in distributed systems, like a zombie machine is like way worse than like a dead machine because you don't know like, should I boot this thing out? Should I keep it in? These are like really hard things to automate. So ideally, you want to like make code changes so they really just can't happen. And in this case, this eventually got tracked down to like locking. There's basically some misbehaving client or piece of Gluster out there that is controlling, that has a lock on a file or directory, and it's not giving it up. And these are also like really hard problems to debug. And because they're hard to debug, it was really hard to write patches for them because we would see this on a system, we would come look at it, we'd do a state dump, we'd see tens of thousands or hundreds of thousands of locks pending, and then you're trying to like piece this all together to figure out like what series of events actually made this happen. So kind of what broke the logjam on this was creating this feature called monkey unlocking. This is like a developer feature. What we do is we actually like on purpose will drop 1% of unlock requests. And this creates these really rare cases into like really common cases. And then the idea was, okay, Gluster must handle monkey unlocking with it on. And it must be able to like not block when this thing is operating. And once we like created this, it actually became like, pretty straightforward on like how to make the patches, how to make sure they worked, and how to ensure stuff like that graph back there never happened. And we created lock revocation. And the idea behind lock revocation is if no one contends for your lock, we're okay, we won't go after you, everything's good. But if anyone is contending on your lock, we're going to revoke you based on two parameters. One is time, the other is how many people are blocked behind you. You can use them one or the other or both, it's really up to you. And it's also POSIX-y. When we revoke a lock, we're going to send you back E again. If you choose to ignore E again in your code, you may crash, that's your problem, not ours. Write V clearly stays in the docs, this can happen. This is why it can happen. And there are the options down there. In practice, we don't see too many people crashing Uni again. We are blessed with pretty good coders, so they're handling it pretty good. All right, final internal change I'll talk about, which is replication. So Gluster actually has, it kind of went through 2 generations of replication. We don't use either of them because one of the things you find when you're trying to like scale things to really large numbers is you need simplicity. So the fewer moving parts, the better. And this was like a case of really that. So we created this thing called Halo replication, which is really a collection of patches that enable this form of geo-replication to take place. First patch, we multi-threaded the heal daemon. This we've given upstream. This could be useful for other people if they just want to make things heal faster. Depending on the hardware using, most people may want to heal slower, not faster, but we have pretty beefy hardware, so faster is better. And this is important when you're like geo-replicating, obviously, because if you're dealing with high latencies, you want to like get as many packets as you can in the air at the same time. The other thing is people come to me and they say, okay, Rich, this is really great. The first question they have is like, what happens when, actually, I'll get to that in a second. Non-destructive GFDD split brain resolution. This will mean nothing until probably the next slide, but it's really important. And basically what it is if you have 2 copies of the same file that have a different GFID, if you're not familiar with Gluster, it's basically like an inode number on a file system, what do you do? And we created a patch to use similar techniques as I discussed on the split brain to resolve these cases. In this case, though, it's non-destructive. We do not, we rename the data. And finally, the Halo feature itself. At its core, it requires only one option. It'll actually figure out for you how many data centers you have. And it will, take its best guess and form replication zones. And within those zones, you will have asynchronous I/O reads and writes. If you're a geek like me, you may want to like tune this. And you can tune things like the minimum number of replicas that you want before you acknowledge a write. As well as the maximum number of replicas you may want, even because maybe within a zone you've got 6 replicas because you're Netflix and you need like a lot of read capacity. So you may limit how many maximum replicas you do synchronously. And then you can decide if you want failover enabled or not, which is enabled by default, which is basically if some failure happens, you can decide that even though there's only 2 replicas in your zone, you may want to bring in another replica from another zone at the cost of higher latency reads and writes, but you want that extra durability. So you may want failover enabled. And also we have this notion of min samples, which is there's at its heart as we look at these pings, and we're kind of this is how we figure out like where all the data centers are. And min samples is like how many pings do I have to see before I actually start making calls? And the system goes in like a synchronous state until that many samples is received. So this is the way you can think of Halo georeplication. We've got like 3 different data centers here. We've got kind of, maybe this is like the West Coast, this is like the East Coast. And on the East Coast, maybe they're 12 milliseconds apart. And then it's like, 65, 70 to the West Coast. And Halo is going to form replication zones based on what Halo setting is set. In this case, it's about 10 milliseconds. So it says anything that is within 10 milliseconds, and this is like the brick nodes themselves. So if you're like an NFS daemon, you're trying to figure out like who should I be talking to synchronously, it's going to do this based on the Halo value. So it's going to say, okay, I can see maybe 20 bricks in my zone, and they're 10 milliseconds away from me. That becomes, I'm going to talk to them synchronously, and everything else, I'm just going to like let the heal daemons do it asynchronously. But maybe you're a weird customer and that's not good enough. And we do have some folks like this that they're like, 1 data center, not enough. I need 2 data centers. Comet hits, takes 1 out. I need my data safe. But I also want a 3rd copy over there for maybe some other reasons. You can actually do this using a fuse mount. And you can actually just say, this is, I want 20 or 30 milliseconds inside for my Halo, and you'll get 2 data centers synchronously. So fundamentally, it's like extremely flexible. And then, of course, we have heal daemons. These are the guys that are actually pushing data between the data centers. And for these guys, they just use infinite halos. So they will see everything and talk to everything and be able to shuttle data around. So just kind of some of the reasons we like Halo, and I think our customers do too. Super easy to use. All the standard tools work. You can use OpenFS, you can use GF APIs, NFS CLIs, and the fuse mounts. It's got some cool behaviors. It's partition tolerant. If 2 regions are up but disconnected, they can both receive writes. And how we do this is actually using that GFID unsplit logic that I mentioned before. Will actually allow you to write to 2 regions simultaneously, and we will be able to handle the case of figuring out like who wins. And when we do figure out who wins, we're not going to blow away the loser. We're going to just rename them out of the way. And we do it pretty much like what a local file system would do, which is like the last writer wins. And it's pretty performant. So 6 hosts, we can get up to 1 gigabyte a second, 450,000 files an hour if you're more interested in files per hour. And this scales perfectly. So if you add 12, 18, 24, whatever, you'll get it. So future work and current challenges, hardware RAID. This is something that we are looking at removing from our stack. We do not know really how we're going to do this yet. It's actually a really hard problem to get rid of NVRAM. So, my first inklings are kind of, I think this may be one of those things that if we can actually solve and get erasure coding into production and really hardened. These guys, Data Labs in Spain, did some awesome work creating the dispersed translator. What we're going to do is try and get that in production on our systems and really, really harden it so it works at our scales. And we're hoping that may be the key to JBOD as well. We don't know yet. And then the other thing is multi-tenancy. We're basically making all of our clusters look the same, act the same. If you become one of our customers, you're just going to get a standardized cell, and you may or may not live with other customers. And another pretty hard problem, because we have to like QoS and provide things like self-service. And we've got the QoS down pretty good. We actually have a patch that we'll be upstreaming probably in this quarter, which is to do throttling at any directory level. And that's kind of been the key for us to get multi-tenancy to work. And that's it. Any questions? Yes. Yeah, so that's cross-country. Yeah. Yeah. And they're both writing the same file. So if they're both writing the same file, and if you're doing the read async, they'll both be reading the data that they're seeing within their region. We allow, so depending on the customer, some people want, they have really, really high consistency requirements. And for those, we have to basically tell them, listen, like you can't really have it all. You can't have, if you want 100% consistency, we can give that to you, but you're going to be in sync mode. So you'll have the geo-replication, but we're really going to have to consult all regions in order to like answer that perfect, to give you that perfect answer to your question in terms of consistency. So. So Gluster is going to, Gluster does granular locking. So as it's replicating that file, it depends. So the very common case is say it's a brand new file. That one's like way more easy. It's, you know, a file might be being written in the West Coast and read on the East Coast. The first thing Gluster is going to do is create a file of some of the, it's going to phallic a fairly significantly sized file, whatever it sees at that moment on the other end, and it's going to begin backfilling the data. Gluster then has like granular locks that it's going to enforce on readers in that region, and they should be able to, they will not be able to read past the lock. So they should actually get pretty consistent reads in that case. The more exotic case would be like the random write case. This is something we just tell our customers, don't do this. We do not really support this. The granular locking in theory should protect you, meaning that while the replication or the heal daemons are actually replicating data into that regional file, it's going to be locked, you won't be able to read it. But this would not be something you're going to want to run like a database on. Like we would tell them like, you know, use database systems have their own replication mechanisms because their requirements are very, very specific. So this is more for like very, you know, like photos or videos or things you open, you write it, and you want it replicated. Go ahead. Not open sourced yet. So we had it pretty down pat on 3.4. On 3.6, we're almost there, I think. But I think 3.6 is really what most of the community is going to want to run it on. So there's kind of a few final things we're kind of like touching up. And like we don't like throwing patches over the fence that are like not hardened. Because since we're like writing the patches, we can run a little bit faster and looser than like an end user. So we don't want to like get patches out there that are really not baked. So yeah, it'll probably happen probably before the Gluster developer summit. We'll get it out there. Yeah. So internal customers. So like WhatsApp might be one of them. Instagram might be one of them. Like these are all to us customers. Yeah. Yep. Yeah, so photo video, to be clear, this is like Everstore, Haystack, this is their bread and butter. We may store bits and pieces of that, but that's usually for like, not for front end access. This is usually like people might be doing like experiments or trying out different, video codecs or these kinds of things. But like, someone comes in and says, I want to store photo video, boom, we shoot them over to the team that is best suited for that. Yeah, go ahead. So it varies on the cluster. I would say the number I do have off the top of my head is probably 80% of the FOPS on a Gluster cluster in our systems are actually metadata. And only 20% are actually reads and writes. In some, it gets as high as 90%. In terms of reads and writes, I think the last time I actually broke down that stat, it was almost 50-50 actually, which actually kind of surprised me because usually on like NFS style systems, it's like, there's usually a lot more reads than there are writes, but for our users, they're pretty heavy. So I think last time I looked, it was about 50-50. Yeah. Like Gluster at Facebook? Yeah, just those 6 guys that were at the front of the presentation. So, yeah. Yep. So currently we depend on our hardware RAID cards to actually do that at a block level. The background scan is all done by the hardware RAID cards at the block level. So Gluster actually has bit raw detection coming. We don't use that yet. What we're probably going to do is roll that into our JBOD project because without hardware RAID, that is something that like you have to own and do. So right now we could pretty much like delegate that to hardware RAID and hope it does its job. Yeah, we actually have, since we run about 20% in ButterFS, it's been a good gut check to see like, is hardware RAID like lying to us? And the answer is not really. Like it's actually fairly rare. We have run into a few cases where ButterFS has pointed out corruptions that the hardware RAID stack did not catch. But they're rare enough that we weren't like concerned. And we've never seen it on 3 replicas. So in these cases, you usually just drop the bad data on that replica and you just reconstruct. No, so not yet. This is something we actually did our own snapshot work using ButterFS. We've done some experiments with LVM to see, like talking to the Gluster guys at the last summit, they seem to be pretty confident in LVM snapshots, and it is like file system agnostic, so it's got some nice properties there. But in our early experiments with it, we were still kind of not super pumped about the performance of it. So our customers are like really, they don't like blocking. Like if anything blocks for almost any reasons, we hear about it. So yeah, at the back. So it can be 100% or it can be 10%. It's really up to the operator of the cluster. We used Gluster as actually, I think, one of the cool things that Gluster designed in, I think, pretty early on is they've got multiple queues for different operations. So you've got high pry queue, you've got a normal pry queue, a low pry queue, and a least pry queue. And you can actually operate heel daemons in the least pry queue. And that enables them to not like suffocate out your production workload. So typically what we'll do is we'll break down, we assign threads to queues based on how many cores our systems have. And then we typically would do like 2 or 3 threads on a least pry queue. So not all of our clusters are running that today because we kind of really only got comfortable with the notion of least pry queuing in 3.6. And 3.4, I think it either worked not so great or not at all. I can't quite remember. But yeah, least pry queuing would be your best bet. Yeah. So if I had to pick, I would probably keep it. Because I actually feel it's like a hard problem that's been like well solved, and I feel like utmost respect for the guys at AdaptTech and LSI. I think these guys know what they're doing and are really good with it. So I think a lot of this is driven by like people wanting more metrics of like what the individual drives are doing. So I think like the message to maybe the hardware RAID vendors out there is like expose a lot more metrics, because there are power users out there that want to know like individual like latencies to individual drives, what are the drives doing, all that kind of stuff. So I think some of that is really driving it from like an engineering standpoint. Yeah. Yep. So the throttling feature that we're putting out is designed to really handle those situations. Now this is brand new to even our team. Typically in the past what we did is if we saw a really heavy hitting customer, we'd actually build their own cell and move them there. In kind of the the new world to really kind of like help us scale is we really need all the cells looking identically. If they are truly big enough, like they're a multi-petabyte kind of use case, they may get their own cell, but it's really by convention, not like from, if you look at our config layouts, for example, it's going to look like any other config. So with throttling, what we'll do is we'll go to a customer and say, hey, how many FOPs do you need? Odds are they're going to be like, what the hell's an FOP? And I have no idea how many I need. So what we may do is be like, okay, run with your workload. We'll then track in their namespace how many FOPs we see, and then we'll say, hey, that's great. This is the cap we're going to place you at before we're going to shunt you to that least pri queue I just talked about. And you know, in some cases they just may need to change their workload because maybe, you know, a lot of cases you see people that are doing like, you know, a 4K read or something. You're like, well, why are you doing a 4K read? And they're like, I don't know. And we're like, well, go look at your code. Because like, you know, sometimes they're so far abstracted using various libraries, they have no idea what like that read actually looks like when it gets down to the syscall level. So. All right, I think I'm out of time, but you can pull me aside and I'll be happy to answer any questions. Thanks.